All right, we're going to look at L'Hopital's rule now. So we don't put these limits in with the other limits because we don't know derivatives yet, because L'Hopital's uses derivatives. So when we are trying to evaluate limits, we try direct substitution first, right? And we might get something with a 0 in the denominator. We might get 0 over 0 or infinity over infinity. And here's just a list of some of these indeterminate forms, right? So we can't do anything with the limit. So the algebra didn't work, or maybe the algebra did work, and we still got an indeterminate form. So what we can do from there is use this rule. So we're going to assume that f of x and g of x are differentiable on an interval a to b, and they contain some point c. And then we also are going to assume that the derivative of g of x is not 0 for all of x in that interval. And then we have, let's say this right here, right? The limit as x approaches c of f of x over g of x. If we substitute in c, we get an indeterminate form. We can then do L'Hopital's rule, which is take the derivative of each one and try again, right? So let's try it. I like to joke and say that L'Hopital's rule is the way you think that quotient rule works. All right, so if I were to directly substitute in 5, I'm going to be left with a 0 in the denominator. So I would try and factor the numerator, and I don't, off the top of my head, see something that factors out. So what we can do is L'Hopital's rule. So we can take the derivative of each piece. So the derivative of the numerator is going to be, let's see, 4x minus 9, and the denominator now becomes 1. And now I can try direct substitution again. So if I plug that in, let's see, 20 minus 9 is what, 11? And I get a value. So the limit is 11. Let's try another one. I guess we could try to rationalize this to see if it works. But I think taking a derivative of each of these pieces might be a more efficient way, right? Because if I directly substitute in, I'm going to get a 0 in the denominator. So I'm going to have to do some kind of manipulation anyway. So let's just take derivatives. So the derivative of the bottom is going to be 1. So just need the derivative of the top. So that is really 4 minus x to the 1/2 minus 3. The minus 3 is not going to matter because the derivative of that constant is 0. So I'm left with 1/2 4 minus x to the negative 1/2. You could rewrite this so the limit as x goes to negative 5 of 1/2 and then square root of 4 minus x. Could do that. I can substitute in negative 5, right? So I'd get 1 over 2 and then times the square root of 9, which is going to be, let's see, 3. So 2 times 3 is 6. So 1/6. That to me was a little quicker than trying to rationalize. All right, a little foreshadowing here. This says the repeated use of it. So maybe we can keep going with derivatives until something works. So let's see. If I were to plug in negative infinity, I'm going to get an indeterminate form. I'm going to get, let's see, infinity, and then, what was that, 1 over infinity? And that's not going to work. So let's do derivatives. So the derivative of, let's see, x squared is going to be 2x. The derivative here will be negative 1 e to the negative x. I don't really need the 1. But if I plug in again, I'll get some form that's indeterminate again. So let's do it again. Limit as x goes to negative infinity of 2 over e to the negative x. All right. If I plug in negative infinity, that's going to be e to the infinity, right? And that's going to give me basically 2 over infinity, which is going to go to 0. Right? So we can do L'Hopital's multiple times until we get an answer. If we keep getting an indeterminate form, then we're going to want to keep going. So yeah, let's try with this one. So the limit as x goes to -2, and we can just keep doing derivatives. So it's going to be 3x squared plus 2x minus 8 over 3x 16x plus 20. I should keep checking to make sure this is going to be an indeterminate form. Let's see, -2, that's going to be 4, so that's 12. 12 minus 4 is 8. 8 minus 8 is 0. 12 minus 32 plus 8. Yeah, I don't know, I said plus 8. Plus 20. Yeah, we'll keep going. All right, so the limit as x goes to -2, and we'll make that 6x plus 2 over 6x plus 16. And then this might work, -2, so that's going to be -12 plus 2, and then -2. So -12, that's going to be 4. And I can reduce that to -5/2. All right. Ooh, let's do some trig and some log functions. All right, if I plug in 1, it's going to give me a denominator of 0. So let's try some derivatives here. So I would get, let's see, 1 over x minus 1, and then e to the x, because e is just a constant. But then if I plug in 1, I'm going to get 0, right? Because if I plug in 1 and 1, I will get, maybe I should do it over here, 0 over e, which is a number. It's just 0, and that's okay. I was debating if I had to do it again. All right. Let's see. I'd get 0 in the denominator, so I'm going to want to try L'Hopital's. All right, so I have a product rule in the top. So left times derivative of the right plus right times the derivative of the left, and then derivative here, 2x. We're still going to get a 0 in the denominator. Sorry, I don't know where my head's at right now. And let's see, is there anything we could maybe simplify? So that's going to be sine squared, and then plus cosine of x minus cosine squared of x all over 2x. All right, so might as well try and do it again. And hopefully this will work out to be something nice. So let's see, that is going to be 2 sine of x cosine of x minus sine of x, and then minus, and we'd have 2 cosine of x times negative sine of x, and then all over 2. I'm just going to rewrite it. So we get 2 sine of x cosine of x minus sine of x plus 2 cosine x sine of x. Oh, but then really, those are like terms. I can combine that into 4. 4 sine of x cosine of x all over 2. If I substitute in 0, right, let's see. Sine of 0 is 0. So that whole first part is 0. Sine of 0 is 0 all over 2. And I get 0. All right. Kind of cool. All right. We get the infinities. Let's see what we can do. All right, I'm going to do a couple of things here. Let's do L'Hopital's, right? So we have the limit as x goes to infinity. And let's just go ahead and go 18x plus 10 over 24x. Still going to get infinity over infinity, so let's do it again. So we'd have 18 over 24. And I think that can reduce. If I do it by 6, I get 3/4, right? But notice, when we go off to the infinities, we're also thinking horizontal asymptotes. So look at the leading coefficients, right? So I can look at that 9x squared over the 12x squared and just look at those leading terms. Well, the x squares, it's like it can cancel out. They're growing at the same rate, right? So I'm left with 9/12, which reduces down to 3/4, right? They have the same degree, so we look at the coefficients, and that reduces to 3/4. And I keep that idea in mind for something like this, right? So I have, if I think about like my order of functions here and how fast things grow, this top one is a quadratic. So it's, it's growing. But then I have e to the x plus natural log of x. So natural log of x, looks something like this. E to the 2x, or really any exponential function, is going to be growing pretty fast. And an exponential is going to grow faster than a quadratic. So right now, if we're going off to the infinities, this one's growing, but this bottom one is growing faster, right? So this is going to go towards 0, but let's do L'Hopital's. So we'd have 8x minus 3, and then I'd have 2e to the 2x plus 1 over x. Then I could go again, right? So I'd have 8 over 4e to the 2x plus, actually be minus 1 over x squared. Right? The more derivatives we do, the more negative that's going to get. So that number here is going to be, this is going to go towards 0, right? And then e to the 2x, it's going to keep growing. So really I have 8 over a really large number, which is going to go to 0. So if we're going off to the infinities, we can look at the leading terms and see which one's growing faster. So look at leading terms and look at, I'll call it a hierarchy if I can spell. All right, so we got 4x squared, and then we have e to the 2x. E to the 2x is always going to be greater than that 4x squared. So we're going to go to 0. let's kind of look here as well, because I wouldn't want to. Maybe you would, but I don't think I do. Want to do a derivative until these things cancel out, because here's what's going to happen. That's going to be natural log of 2 times 2 to the x. And then, let's see, natural log of 2, and then natural log of 2, 2 to the x. And it's going to keep going, right? We're going to keep getting more and more constants. And then this one, you'll have 99, x to the 98. It's already going to be a really large number to do the next one for x to the 97. Continuing on, so forth and so forth. So we can look at that hierarchy of functions again, right? I have an exponential and a polynomial, right? So an exponential is going to grow a lot faster than a polynomial. So this numerator is going to be a lot bigger, and I'm just going to put like this, a lot bigger than the infinity on the bottom, right? So this limit doesn't exist because it'd be a really large number on top and then just a really large number on bottom. So while yes, infinity over infinity is an indeterminate form, we can look at the functions, and that 2 to the x is always going to be greater than that x to the 99. So the number in the end will be infinity, and so that limit is not going to exist. All right, that is all for L'Hopital's rule. So if you have any questions, let me know.